So we're getting down to our last 3 units. This will be 14.3, and we're going to look at how to find an average value. So let's go ahead and get into our discussion here with our further integration techniques. So averages and moving averages. Now we're not going to talk about moving averages. It's not in the homework. We're going to skip over that part. But if you're interested, it's a nice tool to smooth things out as well. But we'll just talk about the average, which also sort of smooths things out. So what is an average? Well, the average is we also refer to as the mean of values that we collect. So what we do is we add all the collected data, all the values together, and then we divide by however many there are. So if there's n things, obviously 1 through n, we divide by n, and that gives us our average. So what does that look like? Well, here's an example. Here's 4 points, 0, 2, -1, and 5. You add them together and then divide by 4. And when you do that, you get 1.5. Geometrically, what that looks like is we had a point at 0, we've got one at 2, one at -1, and one at 5. And the average being 1.5 means that the center is right here. So this is sort of the balance of these points. It's the central balancing. It's not the middle. That would be the median, not the exact middle, but it's going to balance it. So notice if we were to move this 5 out to 6, so it would add 1 more to this. So that would have been 7. 7 divided by 4. It would move this closer to 2 because we're shifting the balance of sort of our weight. And if we were to move it towards 4, we would move it back this way to kind of keep this thing balanced. But that's what an average looks like. It's trying to sort of find a middle ground, a middle place. And so what we're going to look at is what an average looks like in a 2-dimensional world. Okay, so this is a 1-dimensional average. So here's an example. We've got a car that's traveling, at least I hope it's a car, 50 miles per hour to 60 miles an hour. So faster, slower, somewhere between that for 2 hours. And we have this following function that between 0 to 2 hours, this is the function that can be used to show their speed. And notice it's at least 50, and then this adding with t going between 0 and 2, the average speed over those 2 hours. Well, we could calculate the total distance traveled, because remember, if we take the velocity and you integrate it, you get the place function. And when we take a definite integral going from 0 to 2, we'll actually get the amount of distance traveled. So if you integrate the function 50 plus 2.5t squared, you get 50t plus 2.5 over 3t to the third. Remember, we added 1 to the exponent, that made that 3, and then we divided by that. And then so now we go from 2 to 0. So you plug in 2 for t and 0 for t. When you plug in 0 for t, you get 0. So you're subtracting off 0, so there's nothing there. This is 50 times 2 is 100. Put the 2 here, you get 20 over 3. And so when we add this together, we get 106.67 miles. That was traveled. Remember, this is a displacement function now. So what would be their average speed? Well, they did this over 2 hours, so we just need to divide by those 2 hours, right? And that would give them distance per hour, which we call speed. So 106.67 divided by 2, they averaged about 53.3 miles per hour. Again, sometimes faster, sometimes a little slower, but this was their average speed. Okay, so what could that have looked like if we thought of it from the start, right? We're dividing by 2. Notice 2, you can get the number of hours going 2 minus 0. So that's exactly what happens is the limits going from A to B. If you take B minus A and divide by that, you're going to get the average over that time period, okay, or over the intervals. So we integrate, and the only new part of this is we've done this before. This is definite integrals, like 13.4, right? We did this a while ago. All we're adding on is to get the average, we multiply by this factor, 1 over b minus a. So this is going to give us the average. So it's really a straightforward concept that we get going, and then we're also going to look at the geometric implications of this. So whatever function we have, we will get the average value of that function by multiplying by 1 over b minus a. Okay, again, this is the new thing that we're adding today, and all that we're really adding. Okay, so now here's an example. So take the average function f of x equals x. So that's really, y equals x. So that's a function, if you were to graph it, right, that's that 45-degree line, that's y equals x. So if we integrate that from 1 to 5, so 1 to 5, we're getting something like this. That's what the integral is going to be. Remember, area under the curve. And the average we'll expect to be somewhere here in the middle. And what that does is it makes a rectangle. Okay, so it averages it out. And I've got some better pictures of this, but you'll see it. That's what the average will do. Okay, so we go ahead and integrate. X squared integrated is x, when we integrate x, we get x squared over 2. Okay, and then we get that going from 1 to 5. Notice the 1/4 came from 5 minus 1, the limits themselves. And again, that's all we're doing is we're doing stuff we've already done, except we've got this factor out front that we're going to multiply by. So we've done this part before, this here. This is just an indefinite integral, nothing new. We just multiply by 1/4. And so that what we have now is an average value. Okay. And what does that average value mean? Well, let's interpret it. Interpreting the average value of a function geometrically. So let's go ahead and graph this. And I've got a couple examples at the end where we'll go through and we'll do that. So remember, here's this line, y equals x. We took it going from 1 to 5. And so you get this sort of, triangular sort of shape all the way. But what the average function does is it levels it out. And it sort of assumes that it was always happening at that level. A lot of times it's easier to visualize things that are going on. If we go over an average business functions, you want to maybe average out seasonal fluctuations and say, okay, this year, this is what we would expect to happen. Not that the seasonal fluctuations aren't important, but they give you they help you to budget, because most budgets are based on a 1-year basis or maybe a 2 or 3. You've got a certain budget you've got to meet, and this is sort of how you get it. So, and notice these little squares up there are right down here. So what it's really done is it's taken the excess and put it where there was a deficiency and just made a rectangle. That's what the average does for us. Okay, so geometrically. And in the homework problems, you will have to do both. You will have to find the average, like they did here, and then draw on a graph, or choose the right graph is actually what you end up doing. Choose the right graph that has the rectangle drawn properly. So when your answer is equal to 3, then what you're going to choose is the graph that has a line going through 3. It's pretty straightforward. That's really all there is to it. But it's kind of powerful to think that we can get an average simply by multiplying 1 over b minus a. But it works. Even when the function's more fluid, more curvy, the same thing is happening. The average sort of levels out the playing field, and sort of the excess gets crammed into the places where there's deficiencies. and it just levels it out and says it's still the same. The total's still the same. Notice here, this rectangle, we've got the function value times b minus a. That's what it's saying, right? This rectangle here, which is b minus a for the base, times the function value, is equal, it's identical to the integral on the other side. And so what we do is you just divide both sides by b minus a, and that's how we get our function. Okay, that's how we get that formula. Let's go back. The formula way back here. Okay, so this is all we're working with. So we took time to develop it, but it all makes sense. Where did this come from? Because this rectangle, b minus a of f, is equal to this rectangle. And since what we're looking for is this, we solved a little bit of algebra, and that's what we're going to use. So we'll also use our technology. And again, I highly recommend, a graphing calculator is required for this course. It's required. That's why I'm showing you how to use it. Not only is it required, but it's going to make your calculations so much easier. So if you don't have one, I would suggest finding someone to borrow one from or buy one. You can go online. I found some refurbished ones through Walmart that were $60. TI-83, they have the same functions as the 84. You can spend maybe a twice that, to $120 to $130 to get a nice color version, which is helpful. Especially, remember, you're going to go on to that next class. You're going to be successful in this 210, so that you're going to go on to 211, and you'll be using more technology in that class as well. So let's keep moving. We're going to show how we can do this. There's one in the homework very similar to this. So we've got a savings account. It pays 3% interest and compounded continuously. Do you remember from algebra the continuous compounding? The accumulated value is equal to PERT, PE to the RT. PERT. I don't know if they still have that shampoo out. But when I was growing up, PERT was they advertised a lot. So we always remembered in math class PERT, PE to the RT. Okay, so we're going to deposit $10,000 at the beginning of the year. How much interest and how much bonus will you get? And notice the bonus is based on average balance. That's exactly what we're going to be doing, right? So first of all, we use our formula. Accumulated value equals PERT, PE to the RT. P was 10,000, R is 0.03. It's kind of messed up a little bit, but that's supposed to be 0.03, E to the 0.03 T. So we're going to do it for 1 year, plug in 1 here, do the calculation. You find that we've got a total accumulated value at the end of the year of $10,304.55. So the amount of interest we earned, subtract 10,000 from this, the interest was $304.55. So that's an algebra problem. What we want to see is what's the calculus problem that we're doing is we want to find the average value so we can figure out what our bonus is. So we're getting the average over the interval from the beginning when we deposit it to 1 year later. Okay, that is an accumulation. That's an integral going from A to B, which in this case is going to be 0 to 1. And we want the average, so we just 1 over B minus A. Now in this case, B is 1, right? This is A, this is B. So this just becomes 1, so nothing, no calculation there. That's great. There's 1. We integrate this. And again, we can do it with, I'll do it with the technology to show you that, but they're going to calculate it here by hand. So E to the 0.03 T is E to the 0.03 T. Notice we had to divide by 0.03 because of how E works. So we've gone over that integral before. So hopefully you can do this. We could have used U substitution, saying U equals 0.03 T. So du equals 0.03 dx, and notice you get du over 0.03 is what dx. That's where that dividing by 0.03 comes from, just as a reminder. But you're going to want to get where you're more fluid and just saying, yeah, we got to divide by that because it's up here in this exponent with e. Do it several times, and then we take this integral from 0 to 1. Notice when you plug in 0, it might not be obvious. They just did the calculation real quick, but when you plug in 0, it doesn't go away. This becomes 1. Okay. E to the 0 is 1, so we're subtracting this off, but e to the 1 is a number. So go ahead and walk through that, right? It's going, I guess you could say it's 10,000.03, put that out front, but you get e to the 0.03 times 1 minus e to the 0.03 times 0. And go ahead and calculate this one, which is really just, this just becomes e to the 0.03 minus 1. Really? Let's do that. I'm kind of intrigued now. E to the 0.03. I'm just interested, what is that? Oh, it is 1.034. So then subtract 1 from it. We get this factor, 0.03454. And then what are we doing? We're multiplying that times 10,000. That's 100,000. 10,000. And then we're going to divide that by 0.03. 10,151. Exactly what they got. Okay, so it works. It works. So, okay, that's the mathematics behind it. So then you take 1% of this total amount, you get 101. For our problems, we're going to be stopping here because what we're going to be asking for is what's the average value. Okay, so I want to go back and do this one with technology, with the graphing calculator. Okay, so what we would have done, all we needed to do is put this in as 10,000, 1, 2, 3, e, and again it gives me the exponent 0.03x. Okay, now the one thing we got to think about is our interval. So x is going from 0 to 1. That's okay. So I go to my window. I'm going to go from minus 0.5 to 2, just I guess give us a little bit of extra room on the sides. And then, but I got to think of my y. I'm starting at 10,000 and I'm going to get interest. So I better change my y max to something bigger, maybe like, because I know the numbers, 11,000 should work fine. Oops, not 10,000, 11,000. 1, 2, 3. Let's graph it. And again, you see the accumulation value here. And I can go second calc, number 7. I can get the integral between 0 and 1. And it fills this in. There's our 10,151.511. Which in this case really is our average balance, right? Because then we multiply that by 1 and it gives an average balance. So we can see at 1051, it's hard to see here because we're so close. So what I'm going to do is I'm going to take the window, I'm going to just sort of cut off the bottom part. So let's go from 10,000 to 11,000. So we can see the top part of this graph. So this is 10,000, this is 11,000. You know, if we go by a tenth, what we get is that, our averages would go straight across here, something like that. Okay, but this is giving us our average value, and you can get it that way. Let's take a look at another example, and I'm going to use some funky numbers here a little bit. You'll see the homework usually goes from like 0 to 1, 0 to 2. Doesn't make it too bad, so you can calculate by hand, but I want to show you this one. I wouldn't try to calculate it by hand. It's just going to get messy. So what we want to do is we want to find the average of the function over the given interval. So what we're going to do is we're going to graph this function. Excuse me. Allergies getting me already. Again. Okay, so let's keep this big, but I want to move this. So our function, you can see this okay, right? Come over here. Okay, so we put in y equals, let's clear this one out, e to the minus x. And I think there is one with just e to the minus x in there, so I put a plus x squared. Okay, so we graph this. And we're going over the intervals from 0.25 to 1.75. So on my window, yeah, I'll leave it at negative 1.5 to 2. That's good. I've changed my x scale to 0.5. And what I'm going to do is I'm going to go from 0 to, I think I'll go to 4. I think 4 looks good. I've got a y scale of 0.5. Okay. So now when I graph it, I get this happening. So here's 1, here's the full graph. What I need to do is, that's what I, kind of to set this one up. Let's back up because this is the last one. There we go. What I'm going to do is I need the integral from 0.25 to 1.75 e to the minus x plus x squared. And since I want the average, right, we were looking for the average function value, we need to multiply by 1 over 1.75 minus 0.25. That's going to be 1 over 1.5. And what I'm going to do is use my, I should put my dx here. I'm going to use my technology to get this part, and then I'll divide it by 1.5 at the end, and that will be that'll be our value, right? So where's that calculator? So we've got this part. To do this, I just go second calc, number 7. I could integrate this by hand as well and plug in the intervals. But what I want is my lower limit to be 0.25, and my upper limit to be 1.75. And that's what I get. I get my answer is, so let me make sure that this is always in front, is 2.3862. Actually, I haven't divided it by 1.5 yet. Well, I'm going to do it this way, 2.38627. I'll round this last 6. Towards the end, I'll round that up. That should be good enough. And I'm going to divide it by 1.5. That will give us our average value. Okay, and then we're going to come back and we're going to see what that would look like. So let's go do that. 2.386277 divided by 1.5. we get that our average is, come back, I'm not done with you yet. We're not done. Okay, 1.59. Let's remember that. Now it'll let me. 1.59. And usually they want you to round it, I think, to 2 or 3 decimal places. Do whatever they say. 1.591. Okay, so 3 decimal places. Okay, there we go. So then what I want to show you is what does that look like geometrically. I think it's all still there. So geometrically, so here's 1, here's 1, I said 0.5, 1, 1.5. So 1.59 will be a little bit higher. Let's see if I can get a little bit of help here. We're going to draw a line. So what I want is at about 1.6. Let's see if I can do this. Oh, that's right. I gotta now so now this part is on front. So 1.6 is a little bit higher than that. There we go. So here's a straight line across here. Oops, stop. Let's clear it. Let's try it again. Okay, so I'm gonna use a line. Gonna come here. It's gonna be something like this. Okay. Come on. Well, maybe it worked great when I was practicing. So let's go for the freehand. So it comes here. This is about 1.6. Let's go straight across there. It's a terrible rectangle. We went up straight from here. And then from here, you can kind of see that this part here, if you were to cut this stuff and put it into here, that's what you get, is you get this rectangle. Okay, you get this rectangle is equal to the bigger rectangle. That's what the average looks like. So for your homework, there's 5 problems, all very similar to this. You're going to integrate with some limits on it. You're going to do definite integrals. That's a good time to practice using the technology to do that. And then at the end, you're going to multiply by this factor of 1 over the length of that interval, so b minus a, or just divide by it, right? So take your answer divided by it, and this is what you're going to get. This is your answer. A couple, maybe 3 of the problems, you're going to need to choose the right graph, and what you're going to do is, well, 1.59, that's where the horizontal line needs to be. That's all you need to do to get that graph part right. 5 problems, give it some practice. Look back at the 13, I think was it 13.4, the place where we did indefinite integrals. That's really what this is about. And it's just multiplying by that factor of 1 over, or if you want to think of dividing by the interval width. That's all it is. Okay, so keep making your good progress. We've got 2 more sections to finish up this course, and then we'll be into review mode. Thanks, take care, be well, stay safe.